This is the third and last lecture out of Chapter 17 on chemical thermodynamics. And this last lecture is going to talk about free energy under non-standard conditions, as well as the relationship between free energy and the equilibrium constant. So I want to point out to you, you may or may not have noticed that so far when we're talking about enthalpy, entropy, and free energy, we are talking about standard free energy, standard enthalpy, and standard entropy. And the standard is demonstrated with the use of that kind of a degree sign. That degree sign means we're looking for the standard conditions for that. And standard in this case is 1 molar concentration, 25 degrees Celsius, and 1 atmosphere of pressure if we're talking about gases. But it turns out that most of our world is not operating under standard conditions, these perfect set of conditions. Most of the reactions that go on outside of our control are under non-standard conditions, and therefore we have to use a different equation. So what is the relationship between non-standard free energy and standard free energy? Well, it's shown right here. This is an equation I will provide on your exam. But you can see here, if you want to find the free energy under non-standard conditions, you start off with the free energy under standard conditions, and then that value will get tweaked a bit, depending on the Q value. And hopefully you remember what Q is. It's products over reactants, similar to equilibrium constant, except Q has concentrations of products and reactants at any point in time. It does not have to be at equilibrium. So now if you look at this equation, what happens to free energy of a reaction at equilibrium? So let's look visually on what I'm wondering. What happens to free energy of a reaction if we're at equilibrium? So what does that mean? That means if we're at equilibrium, Q equals K. That is true only at equilibrium. And what else do we know about standard free energy at equilibrium? The standard free energy is 0 at equilibrium. So if you remember a graph I talked about briefly in the first lecture from this chapter, I gave you an energy diagram that kind of looked like this V or U, and I told you that if the change in free energy was going down, it was spontaneous, that if the change in free energy was increasing, that would be non-spontaneous. But I also told you that at the very bottom of the valley, that delta G, or free energy, is 0. Okay? It means absolutely no driving force to go either way in this reaction because it's at the lowest energy point. So what happens to this reaction we have, which relates free energy under non-standard conditions to standard free energy, as well as the present concentrations of reactants and products? Well, when we simplify it, that is, when we assume we have equilibrium, okay, the delta G drops out, it becomes 0. And Q, or the reaction quotient, becomes K, the equilibrium constant. Now, of course, these are the conditions that hold at equilibrium, and this is the equation we're most used to dealing with. If you need it in exponential form, if that's easier for you to solve, you can just work with the e's instead of natural logs. So you may want to look through chapter 14 and the very end of it, where it talks about relationship between equilibrium and free energy, because you may get a little bit more theory behind it. All right, so let's look at the math here. I want you to know what to expect for standard free energy, whether it's negative or positive, without always having to do a calculation. So if I told you that the KEQ in this equation, the equilibrium constant, was very small, and let's think about what that means. That means that, let's say if K is less than 1, so it's quite small. What would that mean about the value of the standard free energy? How are these two terms related? It turns out that as KEQ increases, delta G decreases, okay? So let's kind of dissect it and look at a different direction. If KEQ is increasing, what does that mean? That means that we're making more and more product. So we could say products are favored if K is greater than 1. And if products are favored, that means the reaction is spontaneous. And what does that say about delta G? It means it's negative. So what all goes together here? We have, if K is greater than 1, large, that means that delta G is spontaneous. Fits, right? K is greater than 1 means a lot of product, and delta G being spontaneous means a lot of product. On the other hand, if K is less than 1, in other words, if it's small, that means that delta G is not spontaneous, it's positive. Makes sense again. If K is less than 1, that means reactants are favored. That means the reaction's not going very well, and that's because it's not spontaneous. Let's work a sample problem using this equation. So remember, if we're at equilibrium, the equation simplifies. Remember, if we are not at equilibrium, we have a different equation. So let me just write it down so you can see it. If we're not at equilibrium, we're using this form of the equation. All right. So let's look at the problem. What's the free energy? In other words, what is delta G for the reaction shown here? They are giving us the equilibrium constant. It doesn't matter if it's KSP, KA, KB, KEQ. If it's any capital K, it's likely that they're wanting you to use this equation. So we will definitely be using this equation. We're solving for free energy, delta G. We know R is the universal gas constant. All right, so that is the gas constant in joules, and since we're talking about energies, we do want the gas constant to be in joules. And let's see, times temperature must be in Kelvin. And I just noticed I didn't give you a temperature, so we're going to assume standard temperature, which is 25 degrees Celsius. And you get to memorize what that is in Kelvin after doing it enough times, 298 Kelvin. Times log, natural log of KEQ, which they gave to us. 1.1 times 10 to the minus 10. All right, so pretty simple. You just plug in, do all the math, and you get delta G. It's important to remind you of something mathematically here, and I've noticed this from talking to students. I think it has kind of slipped people's mind. If you take the log, whether it's natural log or base 10 log, of any number that's less than 1, any decimal number, it's going to be a negative value. So right away, since I noticed that K is so small, it's certainly less than 1, that I'm going to get a negative value from this log value. And I also know that two negatives are going to give me overall a positive. So I know that ultimately I am going to get a positive or non-spontaneous value for delta G. So just trying to keep you with your common sense here. So what is the natural log of 1.1 times 10 to the minus 10? It is 22.9. All right, so I just wanted to point out that before I complete the calculation. And then when you multiply those all together, you get that the free energy for this is 56.8 kilojoules. Okay, not too hard. Here's another example, kind of working backwards, just to kind of refamiliarize if you're trying to solve for equilibrium constant, how do you get rid of a natural log? So this problem is asking you to calculate K, again, instead of delta G, for this reaction. It's equilibrium, should be double arrow, between dinitrogen tetroxide and nitrogen dioxide. And, of course, they gave you the free energy. Notice right away, so that you have your common sense working with you, that it is non-spontaneous. Okay, delta G has a positive sign, so you should immediately be able to predict the magnitude of the equilibrium constant K. If a reaction is non-spontaneous, if delta G is positive, that means that K will be relatively small, certainly less than 1. Which means that reactants, the denominator, will be favored. Okay, so we're looking for a K value of less than 1. So let's go ahead and plug into the equation that relates free energy and equilibrium. And we were given the free energy of the reaction. Notice that you need to match units. Okay, either use an R value that is in joules, and then change your delta G from kilojoules to joules, which is what I did. Or you could alternatively change the R value so that it is in kilojoules, but you definitely need to match units. Temperature in Kelvin, of course. And when you rearrange that, you see that the natural log of the equilibrium constant equals this conglomerate here, which is minus 1.94. Notice that all the units are gone. Okay, so now how do we get from here, natural log of K equals minus 1.94, to simply K? Well, to do that, if this were log base 10 log, you would raise them to the power of 10. Since it's natural log, we're going to use little e. Okay, so if we raise both sides as an exponent to e, the natural log goes away, and we simply have K equals e raised to the minus 1.94. Now is a good time to check to make sure you locate your e key on your calculator, and go ahead and enter e raised to the minus 1.94. Make sure that when you do that, you get 0.14 as your answer. Well, let's do a calculation for free energy under non-standard conditions. Remember that standard means the substances, if their solutions are 1 molar. If they're gases, they're at a pressure of 1 atmosphere. The temperature is room temperature, which is considered 25 degrees Celsius. So if any of these standard conditions changes, you must use the, you must calculate for non-standard G. So here's one, they're giving you a hint. They're saying they're not running it at 298 K, which right away means it's non-standard conditions. So we are to calculate K both at the standard conditions and at non-standard conditions. You are given the free energy, standard free energy at 298, and the standard free energy at 973. This is a point at which you should pause the video and see if you can work this problem yourself. It's just like the problem we just worked. Okay, so you're going to want the same equation. And you're simply plugging in the values. So go ahead and give that a shot. Make sure you match your units, and when you're ready, go to the next page and see if you did it right. Part B of this problem is kind of a blast from the past. A couple chapters go in equilibrium, but they're giving you concentrations of the reactants and products. And these are concentrations that are not at equilibrium. How do we know? Because the last sentence in that question says, in which direction will it move in order to reach equilibrium? How do we predict direction that a reaction needs to go to reach equilibrium? I don't know if you remember this, but you need to compare Q to K. Okay? And Q, remember, is products over reactants just like K, but Q are the concentrations not at equilibrium, and K has to have equilibrium concentrations. So you simply want to calculate Q by plugging in the appropriate values given for the reactants and products, and then you want to compare the value you got for Q to the value you just calculated for K in part A. What if Q is less than K? Think about what that means. Remember, these are products over reactants. If Q is less than K, that means there's not enough product, right? Which means the reaction would shift toward product to reach equilibrium, to the right. On the other hand, if Q is greater than K, if that means there's too much product. If Q is great, that means there's a lot in the numerator, which is the product, too much product. So if there's too much product, what does it do to get rid of some of it? It shifts toward reactants or to the left. All right, and finally, part C. Once you have determined which way it needs to shift from part B, go ahead and calculate delta G, free energy, non-standard free energy for the system at each of these temperatures. So here's part A. We're going to use our handy-dandy formula relating equilibrium constant and G. And remember, to get rid of the natural log, you raise whatever you have as an exponent to E. So you can either plug into this equation on the left as is and then rearrange it, or you can initially rearrange the equation first, whatever you prefer. All right, so plugging in our values, delta G at 298 was given in the problem, minus 141.6. Pay attention that there's a minus sign in the equation itself, and in addition to that, the delta G value is minus. Okay, so pay attention to sign. Two minuses make a positive. All right, so plugging in the value for free energy, it's in kilojoules. It was given in kilojoules, and because I know that the R value is in joules, I'm going to convert my kilojoules to joules, okay, by multiplying by 1,000. So when we multiply all that out, we get 57.2. This 57.2 is what the exponent is equal to. We still have one more step to do, and that is that K, the equilibrium constant, is E raised to the 57.2. That is huge. Look at the K value. 7 times 10 to the 24th. That is an absolutely huge K value. This reaction is very, very swayed toward product. And since K is very large, we expect the product to be quite spontaneous. And it is. Okay, the value that was given for free energy was negative. Here we go. At both temperatures. Now let's see what happens to the equilibrium constant at a different temperature. Let's first look at what happens to the free energy or spontaneity at different temperatures. At 298, it's spontaneous. Okay, there's a negative sign there, which explains our large K. Now, at an even higher temperature, what happens to delta G? The magnitude of it is much smaller. Okay, it's less negative. Okay, it's still spontaneous because it's a negative value, but negative 12 is a whole lot less than negative 141. Okay, so again, it is spontaneous, but I expect its k to be quite a bit smaller than 10 times or 7 times 10 to the 24th. So plugging everything in, delta G over RT, with units matched and all, e raised to the 1.50 power. So the bottom line, K at 973 Kelvin equals 4.5. Not very big, okay? Just product favored just a slight little bit, which kind of fits with that it's maybe a little bit spontaneous, okay? Not hugely. So this problem might be a little trickier for most of you. This is part B of the problem, and I just restated the question. And probably the red flag you need to notice or make a note of here is that you were given concentrations, okay? So right away that implies that you're going to have to calculate either K or Q. Both of those are products of a reactant. The flag that it's actually Q you're going to need to use is that the concentrations given are not at equilibrium. So the only equation we have that includes Q is this one. So we're going to try to plug in everything we know that belongs in that equation. So first we're going to calculate Q, and it's just like equilibrium constant, in other words, products over reactants. Okay, so I would go ahead and write out the K or Q expression to begin with. The reaction was so that's the equation. And so Q, of course, would be products, which is SO3. And remember, coefficients become exponents. And then reactants, SO2 is one of the reactants, squared, times O2 is the other reactant. Okay. And then I would just go ahead and plug in the values they give you for the different concentrations. And when you do so, the value of Q equals 4. Now you compare the value of Q to K. So now comparing Q to K, we have Q equals 4, and K on the previous slide we found was 4.5. So what does that mean? That means that Q is less than K, which means there are not enough products. Okay? Not enough products, not enough in the numerator, and therefore Q is too small. So what does Q do to, what does it need to do to reach the value for K if it's smaller? Well, it needs to gain more product, which means it needs to shift right. So you can still use Le Chatelier's principle. I hope you can tell there's quite a bit of conceptual understanding in this chapter in addition to the math. So make sure, I would say, spend equal amounts of time on concept and theory as you do on calculations. And finally, almost done, last slide. When you're asked to calculate a non-standard free energy and you're given the standard value, simply plug into this equation. Again, we're solving for non-standard free energy. We know that the standard free energy is minus 141.6 kilojoules. And plugging in for the RT log of Q, here's R. Convert it from kilojoules to joules to match the units. That's 298, which is standard conditions. So 298 is 25 degrees Celsius. And natural log of 4. Remember, this is the Q value. That gives us free energy of minus 138. So compare that to what the standard free energy was at room temperature. let's try to figure out what these numbers mean. When we compare the new free energy to the standard free energy, it gets less spontaneous, okay, a little bit less favorable, okay, because the more negative, the more spontaneous. So it's less spontaneous than it was originally. And look at the value for free energy. Below that, that is still spontaneous, but even less spontaneous. That's it for Lecture 3. That's it for Chapter 17. So remember to review everything in Chapter 17 for your upcoming in-class quiz.